Welcome to Discrete Mathematics tutorial. I'm sure you've come prepared because we are going to go a long way, maybe from the first topic through the most major topics that I think you need help, and then I'll give you maybe just 1-2 topics just to research on yourself. I think it's just 1-2. It's just a few topics that I've left there. So here we are just going to start with the greatest common divisor, which is under the counting unit, which is under the first unit of your module. So the greatest common divisor, it's just like other algorithms. And I know maybe, yeah, I'm sure you've done the module for data structures and algorithm analysis, blah, 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 blah. So we are going to start with what? With the greatest common divisor, this one. So by definition, the greatest common divisor written as GCD of AB. GCD of what? Of AB is the greatest common divisor of A and B. They are saying you are given two numbers, A and B. Then the greatest common divisor is the one which is the greatest common divisor of what? Of A and B, or that larger number that divides into what? Into A and B. Ndoyatoti greatest common divisor. That's what we call greatest common divisor, and it's normally represented by this GCD. So it's an algorithm which was written, which is there, that we can use to find what? The greatest common divisor of given two numbers, I'm trying to see if there are some people that that needs to be accepted. Okay, so that's what we call the greatest what? The greatest common divisor. So what we want you to understand and appreciate here is how to get the greatest common divisor of given two numbers. Just like that. How can you quickly do that using this algorithm? So for example, here, the greatest common divisor of 30 and 105, you are given this 30 and 105. So the greatest common divisor of these two numbers is what? Is 15. 15 is the largest number that gets into both 30 and 105. That's what we mean by what? By saying greatest common divisor. So this is how you write it. GCD of what? Of 30 and 105. This one is A and this one is what? Is B. Just like that. So whenever you're saying A and B, you are referring to these numbers. So let's use this Euclidean what? Algorithm. The Euclidean algorithm to find the greatest common divisor. So there are some algorithms which are there that you can use, but here we are just going to use the what? The Euclidean algorithm to find what? To find the greatest common divisor. And it's the most easy way and easy to understand to find what? Find the greatest common divisor. So there are few steps that you need to master here so that you can what? You can be able to do this on your own. So the Euclidean algorithm is a way to find the greatest common divisor of two positive integers, A and B. So there is this keyword, two positive integers. So this Euclidean algorithm takes two values, which is A and B, and these are two positive integers. So the formal description of the Euclidean algorithm, what you do here, it takes input. The input is what? Is two positive integers, A and B, right? And then the output, it gives the output as the greatest common divisor. that we can refer to as what? As G, which is the greatest common divisor of what? Of A and B. So the input is A and B, and then the output is G, which is the greatest common divisor. So the internal computation, for it to come up with this G after getting these two values, what does it do? So at first, it checks if A is less than B. So if A is less than B, it will exchange A and B. So in other words, this A, we have to be actually greater than what? Than B. So if A is less than B, you have to exchange the values so that you will get the correct value for A. And then after that, you divide A by what? By B. So the smaller value, you divide it into what? Into this A, the larger value. And then what we want there is the remainder. We get the remainder. And if the remainder is 0, whenever you get the remainder as 0, you have to report the current B as your GCD of A and B. Else, you do replace A by what? By B, and replace B by the remainder. And then you return to the previous step. You return to the previous step. So what is here, team? It's just a skeleton of the Euclidean algorithm. So we are just going to do an example. I think it was also part of your assignment. I'm sure we're just going to have something here. And then on that example, we see how you can use the Euclidean algorithm to find the GCD. So here's just an example which asks you to compute the GCD of 210 and 45. So some of the time they do not give you the value of A and the value of B. They'll just give you two integers. Is you have to note that which value is the what? Which value is A and which value is B. And remember, this function takes A and B. So this one, the larger value will be the value of A, and the smaller value will be the value of B. Just like that. So what do you do here? The GCD of 210 and 45. So I want to find the greatest common divisor of 210 and what? And 45. So what do you do there? You say 45 into 210, and then you write it in a form that you write the answer in a form that you place the remainder on its own, and then you write the exact value that you got there as your answer multiplied by this value. So what we are saying here, 45 into 210 gets in 210 4 times, but it leaves a remainder of what? Of 30. It leaves a remainder of 30. So if we say 4 times 45 plus 30, what we get is 210. So you do not need to get confused with this one. So what we are saying here is what? It's 200 and what? And 10 divided by what? By 45. And you are getting a what? You are getting a 4. Remainder what? Remainder 30. Remainder 30. So what we are just doing here, we are just going to write 4 times 45 plus what? Plus 30. Plus 30. So this whole thing is equal to 210. So what we want here is the remainder and this 4. So it will be 4 times 45 plus what? Plus 30. That's what we have done here. So we are just going to do the same. Just need I'm just going to do the same. Terence, can we make sure that we mute ourselves and turn off our cameras?
Okay, thank you.
Yes, okay. So next, what you do there from this statement, which says replace A by B and replace B by R. What you do next here, before, like here, the remainder is 30, the remainder is not 0. So what you do there, you replace B by what? You replace A by B, which means this was our B. So our new A now is the previous B, which is this 45. And then you replace your B with what? With the remainder 30. So it's like you are moving this 45 here and you are taking the remainder up to here. And then you repeat the same process. Then you say 30 into 45. It's 1, remainder what? Remainder 15. It's 1, remainder 15. So what you do there, for you to get 45, it's 1 multiplied by, so 1 multiplied by 30 plus remainder 15. So that's what we get here. That's what we have here. So next, what you do, since our remainder is not 0, our remainder is 15. So what you do from here, since the remainder is not equal to 0, what you do, you replace your A by B and your B by R. So you replace your A by B, which means where there was a 45, it's now a 30. And then you replace your B here by the remainder, which means you replace your B by the remainder 15. So you have 30 and 15 here. After that, you say 15 to 30, it's 2, remainder 0. 15 into 30 is 2, remainder what? Remainder 0. As soon as you get 0 there, that's where you have to report your R as what? As the GCD. So here you can just write this one as what? It's 2 times 15 plus remainder what? Plus remainder 0. Plus remainder 0. So that's what we have here. And whenever you get your remainder as 0, you have to report the B as the greatest common divisor of A and B. So our remainder is now 0. So our B is what? Is 15. So you reported this 15 as your what? As your GCD. So now our G, which is the greatest common divisor, is what? Is now equal to what? Is now equal to 15. So what we are saying here is that the GCD of these two numbers that we are given is what? Is 15. I don't know if there are questions on this one. Is there any question on how you can find the GCD of a given two numbers? Okay, if there is no hand, let me proceed to the next example, which says also we can also use the Euclidean algorithm to solve some sort of equations. So you can apply the Euclidean algorithm and solve. I want to add someone. Okay. On solving these equations of form 182x plus 247y is equal to c, constant c. So here it will be a, maybe it's ax plus by is equal to c. You can solve such type of equation using the Euclidean algorithm. So how do you do it? How do you do that? First, you have to find the greatest common divisor. After finding the greatest common divisor, then you have to do reverse or backtracking. That's how you get to the answer. That's how you get to the answer. So with this one, you are being asked to find the values of x and the value of y, given that 182x plus 247y is equal to the greatest common divisor of 182 and 247. So what you have to do here as your first step is to find the greatest common divisor of 182 and 247. And remember that your A here must be the largest number between these two values. That's why you see here we've got 247 as our A and 182 as our B. So you need to rearrange this first. That's the first step there. Then after that, you have to interchange position, and after that you do what we're just doing there, 182 into 247, and then so it gets into 247 just once, and the remainder, and it leaves a remainder of 65. That's why we have this plus 65 here. So it would be 1 multiplied by 182 plus 65. If you add these things, you get this 247. And after that, remember, your previous B will become your A here, and your remainder will become your B here. And you just do the same, 182 divided by what? By this 65. So it gets into 182 just 2 times or twice, and it leaves a remainder of what? A remainder of 52, this remainder. After that, your previous B will become your what? Your A, and your remainder will become what? Become your B, and you do the same 52 into 65. And then you get what? You get 1, remainder 13. That's why we've got 1 times 52 plus 13 here. And then after that, your previous B will become your A, and then your remainder will become your B, and you just do the same, 13 into 52. It gets into 52 4 times, remainder 0. So it's 4 times 13 plus 0. And remember, when you get the remainder 0, just report your B as the greatest common divisor. So therefore, the GCD of 182 and 247 is 13. That's your final answer there. So now we have the equation which says 182x plus 247 is equal to 13. Why? Because we now have the answer for the greatest common divisor. So after having that, what we'll be having to do now is very simple. You now have to do backtracking here. Just backtracking till you got here. That's how you find the value of x and the value of y. That's how you do it. So how can you reverse this algorithm so that you can find the value of x and the value of y? So remember that for the GCD, like here, you are going to replace this with what? We're going to replace this whole thing with 13, and then you're going to put the equation here. So we have this 13 is 182x plus 247y. So with this one, on our first step here, this is our first step, this is our second step, third step, fourth step, and the final one. So what we are just going to do here is very simple. If you look at this one, finally we've got 3 times 247 minus 4 times 182. You have this one at the end. That's what you have there. But where are we coming from? We are coming from this one. We are coming from this one. Remember, when we say 182 into 247, we are getting 1 remainder 65. We're getting 1 remainder 65. And you look at this one, we've got 65 minus 1 dot 52. 1.52. Just want to see. Okay. I see where I made the mistake. Let me just wrap everything here. You want to do the reverse tracking. Just want to wrap everything. Okay. Just want to do the reverse tracking here. So for you to do this reverse tracking, it's reverse. We have to work from down here up to this point. From down up to this point. So this one, this 65 that we have, so just from this step, because that's where we get the GCD here. The 13 be equal to 65 minus this one times 52. Just like that. We are saying this 30 will be equal to 65 that we have there minus this number here, which is minus 52 or 1.52. Just like this. That's where we are getting this value. That's where we are getting this first statement. I just come here on the last step that we have. We are just taking this A and then you express it in terms of this number. So this remainder will be always equal to 65 minus 1 times 52. I'm sure from the division that we have done, it is quite easier to express this 13 or this remainder in terms of 65 and what we have here. Because remember, we said 52 anopinda kangani muna 65. Tikati anopindeka 1, achisiya remainder 30. Indeed. So tikangoti 1 times 52 plus 30 tinoona 65. So it's now just making this 13 the subject of formula. So you leave 13 here and you put this one to that side. So you end up having this 13 be equal to 65 minus 1 times 52. So just after that, you move on to the next step. So from here, you go to this step. You go to this step. So you're about to use that step. So if you look at this one, we have this 65 minus 1 times 182 minus 2 times 65. Where is this coming from? It is coming from what? From this statement. We are now making this 52, this remainder, the subject of formula. And then we replace this 52 with the value that we get here. We replace this 52 with the value that we get here. So what you have to do there, just need a highlight. Okay. So what you need to do there, this 52 will be equal to what? 182 minus this thing here. So 52 be equal to 182 minus 2 times 65. So do not make a mistake of multiplying 2 by 65 and then you put the final answer. No, just write it just as it is. It will be 182 minus 2 dot or 2 times 65. So we'll be treating this 65 like something like x, right? So do not multiply these things. So it will be 182 minus 2.65. So this one is equivalent to 52. If you actually say 182 minus 2 times 65, you get this 52. So what you do there, you just take this whole thing and put it on this one. So it will become 65 minus 1 times 182 minus 265. So we just replace this 52 by this equivalent value. So from here, I'm sure you can simplify this one by multiplying everything inside by minus 1. So it will become minus 1 times 82. That's what we have here. And then this one become a plus minus 1 times minus 2. It will become positive 2.65. So it will be this 1.65. This one times 65 is not 1.65. It's 1 times 65 plus 2 times 65. So this one is just the same as saying 2x plus x. So you get what? You get a 3x, where your x is equal to what? Is equal to 65. That's why we have this 3 times 65. And then here we've got what? Minus 1 times 82. So from here, you go on to use this final step. So when you get here, you must have your what? You must have your answer. So here we're saying this 247 would be equal to, so this 65 will be equal to 247 minus 1 times 82. That's what we have here. 247 minus 1 times 82 is the one which is equal to this 65. If you evaluate that, you get that 65. So what you do now, you replace this 65 by this, and after that, you multiply everything by what? By 3. So you get 3.247 and minus 3 times 182. And remember, we've got minus 1 times 182. If you group them, it will become minus 1 x or minus x minus 1x minus 3x, because here we are going to multiply by minus 3, and you get a negative 4. You get a negative 4. Sorry, you just get a negative 4. That's why we have 3 times 247 and minus 4 times 182. So what you do here, what you do now with this is very simple. We are now came to our answer. If you look at the equation that we have, is 182x plus 247y is equal to 13. Is equal to 13. This equation that we have. So the coefficient of 182 is our x. So the coefficient of 182 is minus 4, because remember we have got a positive here coefficient. So this minus 4 is x, and then the coefficient of 247 is our y, which is this 3. So that's how you solve this equation using the Euclidean algorithm. That's how. So you can just revise following this slide, and it will be actually easy. I don't know if there are questions on finding the greatest common device. Tina was complaining about the network, saying you cannot hear anything. Is it the same with you guys?
We are hearing
No.
stable.
I can hear you loud and clear from the
We can hear you clearly.
Okay, it's fine. So are there any questions on the Euclidean algorithm? How can you apply it to solve equations? There is a hand by TC. By TC, I don't know what's your name there. You just joined using TC. There is a hand. You can unmute yourself and ask if it is a question or a contribute.
It's Chikotsi Tawanda.
Okay. Okay.
Yes. I think I'm following, but I think I'm a bit lost on the Euclidean format there. But the first part GCD is clear, it's loud and clear. This other one now, the reverse algorithm is where the problem is. I'm a bit lost there.
Okay. What about others? So on the reverse, you are just reversing the Euclidean algorithm. You first work going forward, and then we now want to find the value of x and y, you work backwards. So you just reverse what you have been doing. So if you practice very well on the Euclidean algorithm, finding the GCD, it will be actually easier for you to be able to reverse the algorithm. It will be actually easier for you to reverse this algorithm. It will be very easier. Like here, if you look at these things, just want to do a quick demonstration here. Okay, so if you look at this thing here, what you have is the GCD is what? Is 13. And here you are going to put what? Your 13 here. And then what you are going to do on the last step where you get where you have got your what? Your GCD. Just have to skip this one with the remainder 0. You start on this one. Because remember, on the GCD, it says that when you get the remainder 0, that's where you report your B as GCD. So you just go back to this step. Just go back to this step. So remember, all these numbers are written in terms of A. All these numbers that we have, this and this and this, they are all written in terms of A, of which our A is this one. This is our A. So all these numbers are written in terms of A. So when you're doing backtracking, or when you are reversing this algorithm, what you have to do is just starting here, and you write you'll be writing everything in terms of what? Of this A, which means it will be in terms of 65, 182, up to here. When you get to this 247, you'll be having something in this form, which will be say 182x plus 247y will be equal to 13, something like that. So if you look at this one, we started at this stage. 13 is equal to 65 minus 1 times 52. So you just came here. 65, this 65 is equal to so this 13 is equal to this 65 minus 1 times 52. If you calculate it, you see that it's actually what? It's actually true. It's actually true. Why? Why that? Because when we get this thing here, we said that 52 into 65, and we got one remainder 1 remainder 13. You got 1 remainder 13. And we just write it as 1 times 152 plus 13, which will be equal to this 65. Remember, if you have something of this form, 65 over 52. 52 into 65, it's 1 remainder what? Remainder 13. So you can just say 52 times 1 plus this 13, you can always get this 65. So you can also say 13 minus 65, 13 is equals to 65 minus this 52. You always get this 30. So that's why, that's the working that you have to do there. That's the working that you have to do. So if you look at this one, we've just said 13 is equals to 65 minus 1 times 52. Then next, you just go to the next step. You just come here, and then you express this number in terms of this thing, which means you just say the remainder is equals to 182 minus 2 times 65. But do not multiply these numbers, just write them as they are. So 52, your remainder is equals to 182 minus 265. So what you have to do now is just to come on this step. You want to replace this 52 with what? With what we have on this step. So you replace it with 182 times 182 minus 2 times 65. That's what we have done here. We have just replaced that 52. Then next, you go on to this step, which is the final one. We have this remainder 65. You express it in terms of these two numbers. So 65 will be equal to 247 minus this 1 times 182. And then you replace the 65 with the 247 minus 1 times 82. That's what we have. That's what we have here. That's what we have here. So what we have been doing here, it was just to simplify this thing. That's what we have been doing here. And then you replace this 65 by 247 minus 1 times 82. After that, you simplify and you do not multiply these coefficients, because your coefficients is going to be your answer. So do not multiply these coefficients. Do not like 3 times this way and then you put the total. No, do not do that. So after that, you take the coefficients of 182 and the coefficient of 247. That's the value of x and the value of what? Of y. I don't know if you get it now.
Yes, it's now clear. Thank you so much.
You're welcome. So I'm just move to permutation and combination. Permutation and combinations. So this one is also a topic. On its own, it's also a topic under the counting unit, under the counting unit. So let's start with the permutation. What is a permutation? So by definition, a permutation of n distinct elements, which is x1 up to xn, is an order of the n elements. X1 up to xn. So on permutation, we are looking on how we can order the elements from a given set. How can we order these elements? That's what we call what? Permutation. So here we do look on the order. You are going to see the difference when we do the what? The combinations. When you do the combinations, we'll actually neglect the issue of order there. So on permutation, for example, here there are 6 permutations of 3 elements. If you have 3 elements, there will always what? 6 permutations. If the elements are denoted as A, B, and C, the 6 permutations will be this ABC, and maybe ACB, and then maybe BAC, maybe BCA, and CAB, and CBA. So these ones will become your permutations. So this one, and this one, this one, this one. So there will be 6 permutations there. So you'll be given the elements, and then asked to find maybe the total number of what? Of permutations that you can have from that list of what? Of elements. So the number of permutation of any elements is any factorial. I'm sure you know the issue of factorial. You are given 2 and asked to find 2 factorial. What do you do there? So I think these ones are basic mathematics. So we've got another example which says there are 24 permutations of 4 objects. Like if you are given 4 objects and asked to find the total number of permutations, what you do there, you calculate the factorial of the total number of the objects. And here we are given that the objects there are 4. So you just say 4 factorial. So 4 factorial is just 4 times 3 times 2 times 1, which is equals to what? 24. So those are the total number of permutations that you can get from given 4 objects. So in some cases, we need to find the number of permutations of any elements taken R at a time. So these are mostly type of questions that you see in your exam, or that you see in your assignments, right? Which will be asking you to find the number of permutations of any elements taken R at a time. You'll be taking some number of elements. Maybe you are given 5 elements, but we are saying from 5 elements, maybe just place them as 2 elements. How many possible number of permutations that you can form there? So permutations of such kind use this formula. Use this formula. So you are saying if R is greater than or equal to 1 and less than or equal to n, then the number, so R, it will be the value that you are given, and n, it will be the total number of elements. So then the number of permutations of n elements taken R at a time is n times n minus 1 times n minus 2 up to n minus R plus 1. So the number of permutations of n elements taken R at a time is sometimes denoted by P nr or npr, just like this, which will be this formula. So don't worry, this value will be given, this value will be given. So what you do there, it will be just n factorial over n minus r factorial. So what you need to do there is to be able to identify which is your n and what is your r there, and then just plug into this formula and get your answer. So yes, just an example, which says how many 2-letter words can be formed from letters in the set A, B, C, D if the repeated letters are allowed. So repeated letters are what are allowed. So there is this keyword, how many 2-letter words. You are given your R is what? Is true. Your R is true. You are given your R is true, and then you are given a set with how many elements? 1, 2, 3, 4, with the 4 elements. So it's just the same like the question which was in your assignment, where you are given the word algorithm. The word algorithm is your set. It's just like it was put in a what? In a set and then write algorithm. So it's just the same as writing A, B, C, D. And then we are being asked to find the total number of permutations that we can have there. So the two letter words are AB, AC, AD. So this one is the list of words. But what we want actually is the total number of permutations that you can have there. So the total number of permutations is from this formula, PNR, which is equal to n factorial over n minus r factorial. And your n is the total number of elements, which is 4, and your r is 2, which you are given here. So what you do there, you just say n factorial over n minus r factorial, which is equals to 4 factorial over 4 minus 2 factorial, which is equals to 4 factorial over 2 factorial, which is equals to 4 times 3 times 2 times 1 over 2 times 1, which means you can cancel this one and this one. You're left with the 4 times 3, which is equals to this 12. So what you have there is what? Is 12 as your answer. That's the total number of permutations that you can form there. So there is this exercise, which was asking you, I'm sure this one was also part of your assignment. One of these two, I'm sure one of these two questions was part of your assignment. So just revise all these things. Okay, so how many ways can 5 of the letters of the word algorithms be selected and written in a row? This one is a question. How many ways can 5 of the letters of the word algorithm be selected and written in a row if the first 2 letters must be TH? Must be TH. So for the first one, there is the way that you have to go around, and then for the second one, maybe there will be some slight changes, but it's just what the formula is just the same. So you are being asked the ways we can write 5 letters from this algorithm, from this word algorithm. So you just select 5 letters here, and how many ways can you write those 5 letters? I just select 5 letters here. So what you do there, remember this one is our what? Is our set. This algorithm is what? Is our set. And this 5 is what? Is our R. So this one is our what? Is our R. And this one will give us our N. And then you just plug into your formula. So you need to count the letters in this word. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So your N is 9. So this algorithm will become your set, and then this 5 will become your R. So from this formula, we have n factorial over n minus r, which will become 9 factorial over 9 minus 5. So what we have there is 9 factorial over 4 factorial, which will give you these values. If you look at this one, you have got 9 times 8 times 7 times 4 times 5. And then the rest numbers are not here, like from 4 to 1. Why? They will be cancelling each other with the 4 factorial, which will be underneath here. Was 4 factorial, it will be 4 times 3 times 2 times 1. So it will cancel each other with the remainder numbers that were supposed to be on this 9 factorial on the top. So you only left out with what? With the 9 times 8 times 7 times 6 times 5, which will be equal to 15,120. So that's the total number of permutations that you can have. So this one is just the solution of this question A. What about this one, which says how many ways can 5 of the letters in the word algorithm be selected and stay in a row if the first 2 letters must be th? Remember, here you are given the first 2 letters. So you are going to select 5 letters, and when you come up with your 5 letters, the first 2 letters must be always th, which means from a 5-letter word, you are left with what? We are left with 3 positions that you have to put the words, but otherwise the letters. But otherwise, the first 2 is what? Is th. The first 2 is what? Is th. So how you solve this one? You just solve it by reduce your n. By reduce your n. How do you reduce your n? So since the first 2 letters must be th, hence we need to choose the remaining 3 letters out of the letters out of the left 9 minus 2, or out of the left alphabets. Out of the left alphabets. So here we have an algorithm, but we are going to remove this th and put it aside, and then you're left with 1, 2, 3, 4, 5, 6, 7. And after that, what you do there, after that, you have your new n, right? Your new n is now what? Is now 7. And you have th here, so you are just going to pick only 3. So this will become your what? Your new formula, which will be 7, 3. So your n will be 7 and your r will be 3. So it will now become 7 factorial over 7 minus 3. And then from there, so it's like you are saying, okay, this 7 minus 3 is what? Is 4. So it's now 7 factorial over what? Over 4 factorial. That's why you see that here for 7 times 6 times 5. Just because the 4 factorial at the top, we cancel with the 4 factorial at the bottom here. So you are going to have 7.6.5. This one is a 6. And then dot maybe 4, 3, 2, 1. Then all over 4 factorial. So remember your 4 factorial, it will be 4.3.2.1. So this one and this one will cancel each other. That's why we have got 7 times 6 times 5. And which is equals to 210. So this is how you do this. This is how you answer this question, and that's how you answer this question. I don't know if there are questions on the permutations. On the permutations. Do we have any question on permutation? TC.
It's not in relation. I've mastered this concept. My issue is it allowed if I can use the calculator direct without following format?
Yeah, it's allowed to use the calculator direct, but what if you made a mistake on punching the figures on your calculator, and then you give me a wrong answer? Maybe I was going to give you for giving all these explanations, because it's actually tricky for you to come up with this one. And then I just saw you have just put the answer here, and maybe you put the wrong answer there. What do you think you get then? How many marks do you think you score?
Definitely it's a 0.
Exactly.
Thank you.
Exactly. So just try to write everything. Maybe you have to write everything like what I've done here. And then you just actually show that you know what you are doing. And we do appreciate that, and we do appreciate that effort. So it's actually wiser to do that. And then I saw a hand on Locati. You can just unmute yourself and contribute if you've got a contribution, or just ask your question.
Okay, thank you, sir. It's a question on this exercise part A. So does it mean that we treat every single letter of the word algorithm is is one letter of the alphabet? I think I'm lost there in A. B, I understand the concept.
Or the A.
Yes.
Come again. What was your question?
My question is this one, A, it says how many ways can 5 letters of the word algorithm be selected and written in a row? The first one that you taught us, it was a set of A, B, C, and D. So I was asking if we treat these words of these letters of the word algorithm as 1 word, 2 word, 3 word. These ones are what? 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yes.
Oh, okay. I get it now.
Okay. So that's what's the patati A, B, C, D, patati A, B, C, D. Ndova tungoti algorithm angofana ngoti ari muset. So tungoti A ileta rimwe chete, A ileta rimwe chete, G ileta rimwe chete. Anenge 1, 2, 1, 2, 3, 4 vachikusvika ku9, anenge ari 9. Ma-elements akapiwa ari muset. Ndokuti zviite simple.
Okay, thank you.
Okay. So let's move on to combinations. This one we are just going to browse through. There isn't much that we need there, but it's just preparing you for the future. So on combinations, by definition, a combination of n elements, which is from x1 up to xn, taken r at a time, is the selection of r elements where order does not count. So on a combination, order does not count. We just want to combine the elements in any manner, but the order does not count. So for example here, there are 4 combinations of 4 elements, taken 3 at a time. If the elements are denoted ABC, we've got the elements as A, B, C, and D. And then the 4 combinations will be as ABC, ABD, ACD, BCD, just like that. So what we are saying here, the order does not matter. You'll be just writing the combination of 3 letters. So ABC and ACB is just one thing. ACB and ABC is just one thing. The order does not work, does not matter. So that's why you've got just ABC, ABD, ACD, and BCD. That's like that. So the number of combination of n elements taken r at a time is now n factorial over r factorial, n minus r factorial. So this one is the formula for what? For combinations. Your n is just the same as in a combination, and your r is just the same as in permutations. The way we define these parameters in permutation. It's just the same.
The screen is not showing what you're explaining.
The screen is not showing.
It's showing.
It's showing now.
Not showing on my side.
Okay.
There are
On
still
my side,
permutations, not combinations.
I'm on
it's on
combination.
combination.
I'm on combination.
Okay.
So I don't know. I don't know. Are you seeing my slide?
No. We are
Okay.
still
No.
seeing the exercise. Yeah.
Okay,
Yeah,
it's
this
fine.
side is okay.
Let me reshare. What about now?
I can
No,
see it.
it's not showing.
Myself,
This
I can
network.
see
Because I
everything
can
is just
see here.
It's showing combinations.
It's still showing the exercise.
Mine is
So
still showing exercise also.
yeah, I think it's now your network. So,
this side we are following. Everything is just okay. Even the screen is okay.
I think it's now the network. For those who are not actually seeing where I am, maybe just need log out and log in. Just log out and log in, but do it quick. Because I'm sure it's now on your network. It's now on your network site. Okay, so that's the formula that you use. That's the formula that you use. So this one is an example. How many committees of 3 can be formed from 7 people? There are 7 people, and you want to form a committee of 3 people. So how many? So you are saying there's Susan, there's Vimbai, there's what, up to 7 people. And want to place them into what? Into a committee of 3, 3, 3. So how many possible combinations that we can come up with? Same group. So how many possible combinations? That's what we call what? The combinations. So the solution, each commit is a combination of 7 people taken 3 at a time. So that's the number of committees that can be formed is 35. So the total possible combination that we can come up with, or the number of committees that we can form here, is 35. How do we get that? Your 7 here is your N, and 3 is your R. So it's just the matter of substitute. So you substitute your N and your R here. So 7, 7 on N, 7, and then on R, you put on your R, what do you put there? You put your 3. Just like that. You put your 3 here. So you just solve this one. You see that you can cancel this whole thing and this whole thing. And then you're left with 7 times 6 times 5 divided by 3 times 2 times 2. And you get your 35 there. That's the total number of combinations that you can come up with. So that's it on combinations. That's it. I don't know if there are some questions on combinations. There are questions on combinations.
Sir,
Yes, Mapos.
on your calculation, there is it like on 3 factorial bracket? Is it 3 times 2 times 2, or should be times 1?
On this one.
Yes.
Oh, okay. 7 minus 3 is 4 factorial, which is this one, and then 3 factorial. Okay, yeah, this one is supposed to be 1. This one. Thank you for that correction. It's 1. It's a 1 there, and I'm sure that the result will be 35, but it was a typo here. It was a typo. Thank you for that. And there was a hand by Christina.
Yes, sir. You moved on quickly before I could ask. It's actually from permutations.
Permutations.
Yes. What if you have say you have repeated letters in a set?
You have got what? The repeated
Yes,
letters.
yes, repeated letters in a set.
Okay, okay. That scenario.
Yes.
What do you do with that scenario whenever we have got repeating alphabets, like in algorithm here? If you have got, if there was another M, what were you supposed to do? So that one is a matter of not confusing others or what. It's quite easy to counter for that. It's quite easy. You can just do a simple Googling on that one, because it's a scenario that we mostly not encounter here. But just go to Google that one. It's actually easy. But let's just now stick to what we have here. Let's just stick to what we have here. For that one, you can do a simple Google. It's just simple. You can follow a simple video. It's not that much. I know it's not that much, but let's just leave it for now. Let's just focus on what we have here. Yeah. I don't know if there are other questions. Because when I was preparing this tutorial, I was also thinking about the time that we are left with. Okay, so if there are no questions, I'm trying to speed up so that we can finish this tutorial. So let's talk about the Pigeonhole principle. Let's talk about the Pigeonhole principle. What do you understand by the Pigeonhole principle? What do you understand by the Pigeonhole principle? I don't know if there's someone who want to come in on this one. The Pigeonhole principle. Pigeonhole principle. Was it not in your assignments, guys? The Pigeonhole principle. Okay. So the Pigeonhole principle is a mathematical principle that states that if any items are put into K containers with n greater than K, then at least one container must contain more than one item. What we are saying here is that you are given the items that you want to place into containers, and the number of items is greater than the number of containers. So you are saying after placing each and every item in its own container, you are going to have a container which is going to have more than one items. That's the Pigeonhole principle. Like here, we have got 1, 2, 3, 4, 5, 6 walls that we have, or containers that we have. And you want to put the pigeons in what? In each and every container. And the pigeon that you have is 1, 2, 3, 4, 5, 6, 7. So if you place one here and one here and one here and one here and one here, you are left with the 2. So those 2 will be in what? In this container or in this wall. So what you are saying, whenever you are given containers or K containers and given any pigeons where the number of pigeons is greater than the number of what? Of walls, then at the end you are going to have a wall which is going to have more than one or at least one pigeon. So that's the Pigeonhole principle. So if you are being asked to prove the Pigeonhole principle, you actually asked to show that you can to show that whenever you are given a K containers and n items which are greater than the number of containers, you are always going to have a row which is going to have at least one pigeon, just like that. So pigeonhole principle. So if any pigeons fly into K pigeonholes and K is less than N, some pigeonhole contains at least 2 pigeons. It's just written vice versa, but it's just the same as this one, N greater than K and K less than N. It's just the same thing. So for example here, 10 people, a first name, we've got 10 people with the first name Arnold, Ben, and Alan, and last names is Razambo, Farhan, and Moy. Show that at least 2 people have the same first and last names. So you are given these first names and last names. And you are being asked to show that at least 2 people have the same first name and last names. So what could be your solution there? So here there are 9 possible names for the 10 people. Like here you are given Arnold, Ben, and Alan. So from Arnold, Ben, and Alan, and these last names, how many possible combinations that you can come up with? Matching the name and what? And the surname. Those ones, if you do it well, you will get 9. If we think of the people as pigeons and the names as pigeonholes, we can consider the assignment of names to people to be that of assigning pigeonholes to the pigeons. By the pigeonhole principle, some name pigeonhole is assigned to the least 2 people or pigeons, which you confirm what? Which you confirm this with at least 2 people. Because remember, we've got 9 and 10. So if you place 10 things into 9, you are going to have one container which is going to contain 2. Just like that. You're just going to have just one row with what? With the 2 items. It's just the same. We've got another example here. Just to do the same with this example, which says among any group of 367 people, among any group of 367 people, there must be at least 2 with the same birthday. What you are saying, you have got 367 people. All these people, there must be at least 2 people with the same birthday. Why? Because a year have got 366 days, which means we've got 366 possible birthdays. We have 366 possible what? Possible birthdays. So whenever we go to 367, which means there's this person which you have the day, which will be always the same as someone who is within these 366 days. So for you to prove that, that's what we have to state there. You have to state that we have 366 possible birthdays in what? In 366 days or in a year. So whenever we add the person from 366 people, that person that will come for this 367, that person is going to occupy the birthday of someone. So that's how you can assert this on the pigeonhole principle. Then here there is this one which says in any set of 27 English words, we have got 27 English words, there must be at least 2 that begin with same letter. Since there are 26 letters in the alphabet or in the English alphabet. So in the English alphabet, which is A to Z, we have got 26 letters. So if we have 27 English words, we are sure that there will be one word. There is a possibility of having what? One word. So the two words which you start with what? With the same letter. There will be two words which will be start with the same letter. Because from these 26 letters, if we put from A to Z as the initial letter, it means the word at number 27 will always pick maybe any letter from A to Z. By doing so, we end up having two words with what? With the same letter at the beginning, which means we managed to prove the pigeonhole principle. That whenever you are given pigeonholes, any pigeonholes, maybe K pigeonholes and N pigeons, you always have the pigeonhole with at least two pigeons, with at least two pigeons. So remember, there is a hand on Mr. Sosa.
Yes, sir. I wanted to say that your screen is not showing like the one you're explaining.
Okay, what about others? I think
This side is
this side is okay.
This side.
I think Miss Sosa, you can quickly log out and log in. I'm sure it's just the network on your side. I don't know if there is an easier way of refreshing that, but I'm sure that's the issue there. Because even if I miss A,
I can't see. I'm seeing the last exercise of permutation.
I am sure let me try to reshare. Let me just try to reshare and see if you have something. What about now?
Still nothing. Let me try to rejoin it.
What about now? Are you seeing Mr. Sosa?
I can't see anything. I'm still seeing the same exercise on permutation. So let me re-exit and rejoin, I think.
Yeah, it's okay. That's the best that you can do there. Are you in now?
Yeah, now it's now working. Thanks.
Okay, it's okay. It's okay. So there is this example which says what is the minimum number of students in a class to be sure that two of them are born in the same month. So we are saying we've got a class. So how can we be sure that in this class two of the students in that class are born in the same month? So what you do, just went for the worst case scenario here. You know that in a year we have got 12 months. So for you to have that possible scenario of having two students sharing the same month, it means we need more than 13 students. We need more than 12 students. We need more than 12 students. By just placing the student 1 maybe on January up to student 12 on December. So the 13th student will always occupy any month from January to what? To December. By doing so, we end up having two students having the what? The birthday in the same month, or born in the what? In the same month. So the solution here there are 12 or n months in a year, and the Pigeonhole principle shows that among any 13, which is n plus 1, or more students, there must be at least 2 students who are born in the same month. Just like that. So that's how you put it there. So there is this example. I think this one was also in your what, in your assignment, where it says let A be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so A is just a set with elements which are numbers between 1 and 10 inclusive. So the question goes on to say, suppose 6 integers are chosen from A. Suppose 6 integers are chosen from A. Must there be 2 integers whose sum is 11? Must there be 2 integers whose sum is 11? So we are going to pick 6 integers. If you pick 6 integers, from those integers, just show that there must be 2 integers that will give us the sum as 11. So how do you show that? How do you show that? Or how you can ensure us that if we pick 6 numbers from those 6 numbers, we can actually pick 2 numbers that can give us the sum of 11. So for you to be sure of this, what you do, you have to place all these numbers into smaller sets. That gives you the sum as, or the total sum as what? As 11. So you check the possible numbers that can you give 11. So if you take 1 and 10, 1 plus 10 it will give you 11. 2 and 9 it will give you 11. 3 and 8 it will give you 11. 4 and 7 it will give you 11. 5 and 6 it will give you 11. And if you count on these sets, is what? This total number is 5. 1, 2, 3, 4, 5. So here, if you pick maybe 1, 2, 3, 4, and 5, and whenever you are trying to pick the 60 number, you are sure that that 60 number, if I put it in this set, it is going, I'm going to have 2 numbers in that set that will give me 11. Because if you just take these first, maybe these first numbers, and then you pick any from these second numbers, we are sure that we have a chance of matching that number that you are going to pick with the first 5 numbers that we have picked, and then it will give us the sum of what? Of 11. So these 5 subsets can be considered as 5 pigeonholes. And if 6, which is 5 plus 1 integers are selected from A, then by pigeonhole principle, at least 2 must be from one of the 5 subsets. But then the sum of these 2 integers is what? Is 11. That's how you prove the pigeonhole principle on this one. That's how you prove the pigeonhole principle on this one. So you do a revision there. Just do a revision there. I don't know if there are questions. I'm sure we are about to do proofs. So that's all on the pigeonhole principle. That's on the pigeonhole principle. Do you have any questions? Okay, so let's move faster because it's now about almost 2 hours in this tutorial. So we have a long way to go. So let's do proofs, methods of proofs. So on proofs, we're going to do direct proof and the indirect proof. On indirect proof, we are going to do contraposition and contradiction. And after that, you do the mathematical induction, though it's a chapter on its own. It's a chapter on its own, but it's also a method of proof, which is the mathematical induction. So after finishing those methods on the proofs, we will be done with proofs. So we are going to start with direct proof. So on direct proof, there isn't much on direct proof. What you have to know here, there are some, or there is terminology that you need to understand. There are some basics that you need to understand on direct proof. If you are good with such basics, you'll be good to go. So the implication, which is P implies Q. I'm sure you've done this in your mathematical foundation module. By then, I think you were doing it with the Mr. Map. I'm sure you've done all these things. So the implication, P implies Q, can be proved by showing that if P is true, then Q must also be what? Must be also true. This shows that the combination of P true and Q false never occurs. So what we are saying here, P implies Q is that when P is true, also Q is always what? Is always true. So when P is true, Q is what? Is always true. That's P implies Q. So what we are saying here, on direct proof, if we prove that P is true, it also implies Q what? Q is true. So there are some basics on direct proof. And what is most important to know here is the one for even, integer, odd integer, prime, maybe irrational, maybe perfect square, maybe the divisibility. But what I'm saying is, for it to be easier for you, what is very important are these basics for it to be easier for you. So maybe you can go through the whole list, but those what I highlighted are the most prominent basics that will be mostly used in your questions. So an integer n is even if and only if n is equal to 2k for some integer k. So you are saying n is always even if we can have some integer k that if we multiply it by 2, we always get an n. So any number being said to be even, it must be expressed in terms of what? Of 2k. And any integer which is said to be odd is odd if and only if it can be expressed in terms of 2k plus 1 for some integer what? For some integer k. So we are saying for it to be odd, you must always have 2k plus 1. Like for example, 3, you can say 3 is odd because we have got 2 times k, which is 1, and then plus remainder 1. So our k will be 1. So 3 is odd because we can express it as 2k plus 1. Just like that. You can do the same. 2 is even because we can have 2 times 1, which is 2k. Even if it is 4, 4 is even because we have got 2 times 2, where our 2, the second 2 will be equal to what? Will be equal to k. So that's it for the even and odd. And then for the prime numbers, an integer n is prime if and only if n is greater than 1. And for all positive integers r and s, if n is equals to r times s, then r is equals to 1 or s is equals to 1. And then you can read on this up to here to the perfect square, where we say n is a perfect square if n is equals to k squared for some integer k. So let's see, but on this slide, we're just going to use maybe these two. So prove that the sum of two odd integers is even. So you are being asked to prove that the sum of two odd integers is what? Is even. So you are not given anything, but you are given this keyword, odd integers. So you are just going to take two integers, and then if you add, not just integers, two odd integers. And if you add those odd integers, you need to show us that the result is even. Like for example, if I say 3 plus 5, you get what? You get an 8, right? So 3 plus 5 is equal to 8, which is what? Which is even. So this is what we want you to what? Want you to show. So how you can show this? You need to pick your two odd integers, right? And after picking two odd integers, and then you add them. So let's say we've got these two integers as m and n, these odd integers. So then by definition, odd numbers, m will be always in the form of 2k plus 1. For some k is an element of z. And then n will be equal to 2l plus 1 for some I, element of what? Of z. No, not I. This one's an L. So what we are saying here we've put an L and here we've put a K so that we can differentiate these two odd integers. So this one is an odd integer because it's written in this form. And then this one is also, so these two are two different odd integers. So we want to prove that if we add these two odd integers, the result will be even. So adding these, it will be m plus n. So m plus n will be equal to 2k plus 1 plus 2l plus 1, which means by addition, you can add these two, you can also add these two. You are not multiplying, you are just adding. So by adding, if you remove these brackets, you get 2k plus 2l plus 2. Because this 1 plus 1 will be always equal to what? To 2. After that, you can factor out these two. By factor out these two, you get 2k plus l plus 1. If you look at this, you see that this one is an even number because it is in form of what? It is in this form of 2k, where k is something which is here. So if we multiply this something by 2, which means that thing is going to always be even. So any number multiplied by 2 is always what? Is always even. Be it a multiply number odd, one way multiplying by 2 is always what? Is always even. So after that, you get what? 2r, where your r is equals to k plus 1, r plus l plus what? Plus 1. So hence m plus n is what? Is even. So this is how you do on the direct proof. This is how you can actually prove that m plus n is even. This is how you can prove that m plus n is even, or the sum of two odd integers is even. I don't know if there are questions on this one. So if there are no questions, let's just do the proof by contradiction. The proof by contradiction. I just limited the examples here so that we can finish this slide. So let's do the proof by contradiction. So this one is now a bit trick, like the opposite of the direct proof. What you are supposed to do here, you have to oppose, or you have to flip the assumption that you are given, and then after that, what you get, or the answer that you get, it must contradict with the initial statement that you made after flipping. If it does contradict, zvinoreva kuti zvona izvo the initial statement yawakapiwa inenge iri true. So a proof by contradiction is based on the fact that either a statement is true or it is false, but not both. So what you are saying here, the statement is either true or false, right? So if you flip it to be false, let was not chishuwa chabva chabuda chiri false. Noreva kuti chinhu ichocho chiri false. Pakachiflipa chobva chaita false, chobva chabuda wobva chiti chiri false, chobva chabuda chiri true. Zvine zvakureva kuti zvinhu zvaita contradict with the initial statement. So as the supposition here that the statement to be proved is false leads to a logical or to logically a contradiction, then the supposition must be what? Must be false. As the given statement must be true. So that's what it is. Maybe it would be easier if you do a what? If you do a example, then it will be easier if we do what? An example. So many theorems in mathematics are conditional statements, which P implies Q. So the negation of the implication P implies Q is P and negation of Q. So that's to prove an implication P implies Q by contradiction method. We suppose that the condition P and the negation of the conclusion Q is true and ultimately arrive at what? At a contradiction. So you first create a supposition, and then if it contradicts with the original statement, and then you actually say that the original statement was true. But if it does not contradict, you just say that the original statement was false. That's what you have to do then. So the steps are summarized as: suppose the statement to be proved is false, and they show that this supposition leads to a logical or to logically to a what? To a contradiction, and then conclude that the statement to be proved is true. So you just give an assumption or a supposition that the statement that you are given is false, and then you try to prove that it is false. If it actually leads to a contradiction, then you just say that the given statement was actually true. So how do you do that? Here's an example which says give a proof by contradiction for the statement: if n squared is an even integer, then n is an even integer. So we are saying if n squared, the result that you get on n squared is an even integer, then n is a what? Is an even integer. So if you just say, just for example, if our n is 2, so if we say 2 squared, you get a what? A 4. So whenever you get this even, which means this n, our n, which was 2, is what? Is an even. Those are true ones. Just prove that if you get this perfect square of n, which means your n is what? As even integer, which means your n is also what? Is also even. Like if I put 3 squared, I'll get a what? I'll get a 9. And 9 is not what? It's not even. And this 3 is what? You see that this 3 is not what? It's not even. So it's like something which is true, but maybe how can we prove that? So that we prove for every what? For every integer, that if n squared is even, hence n is what? N is even. So you are being asked to use you are being asked to use, just want to write a few bit. You are being asked to use the proof by contradiction. So first, we said that you have to give a supposition. You have to suppose that the statement to be proved is false. So suppose n squared is an even integer and n is not even, so that n is what? N is odd. You see what we are saying? We are supposed to prove that if n squared is even, then n is what? N is even. But here we are just going to flip that and try to prove that if n squared is even, then n is what? N is odd. That's the first part of it. You have to give, or you have to suppose that the statement to be proved is what? Is false, right? And after that, we now have our n is what? Is odd. So if n is odd, it will be in the form of what? Of 2k plus 1. Remember those basics. So our n is equal to 2k plus 1. And remember, n is now n is squared. You want to prove this n is squared with what? This, if n squared is even, and then n is what? N is odd. So we are taking this n is odd, and we square it and see if we are going to have the even integer. So it will be 2k plus 1 squared, which is 2k plus 1 times 2k plus 1. If you multiply that and simplify, you all end up having this one. So it will be 2k times 2k, then 2k times 1, and then 1 times 2k, and 1 times 1, and then we add everything. You are going to get 4k squared plus 4k plus 1. After getting this, if you factor out 2 here, you are going to have 2 times 2k squared plus 2k plus 1. So if you take this one as r here, this everything is r, you end up having something in the form of 2r plus 1, which is an odd number. So any squared about the odd number instead of even number, those are it leads to a contradiction. So this shows that any squared is odd, which is a contradiction to our supposition that any squared is even. Hence, the given statement is true. The given statement is true. If I using what? Using contradiction. I don't know if there is a question here on contradiction, because I'm sure this example is enough for this. Is there any question on proof by contradiction? Okay, so if there are no questions, let's do proof by. There are no questions. Let's do proof by contraposition. There is contrapositive, or the contraposition. It's now from the contradiction, it's now contraposition. So a proof by contraposition is based on the logical equivalence. It's based on the logical equivalence between a statement and its contrapositive. So you just need to take the contrapositive of a statement and then prove if it is true, so that you can assert that the given statement is true. So therefore, the implication P implies Q can be showing that its contrapositive is the negation of Q implies the negation of what? Of P is true. So the contrapositive of this system, P implies Q, is contrapositive from your mathematical foundation, is that the negation of Q implies the negation of P. So you have to prove this. After proving this, you can now make conclusion on this one. So the contrapositive is usually proved directly. So on contrapositive, what you need to do there is to follow these steps, but on solving it, you use the direct method. So contraposition, contrapositive, it's just the same as the what? As the direct method, but only that there are some of things that you have to first do there. So what you have to do first, or the steps that you have to follow, express the statement in the form of P, then Q, or P implies Q, and then rewrite this statement in the contrapositive form. If you not Q, then not what? Not P. And after that, prove the contrapositive by a direct proof. So this is what you have to do first. After that, direct proof no. My basics and everything. Data topens. So on proof by contraposition, this one is the example. Prove that for all integers n, if n squared is even, then n is even. So if we have that example. So how do you prove it? Contraposition. So the contrapositive of the statement of the given statement is if n is not even, which means if n is odd, then n squared is what? Is odd. Remember, if n squared is even, then n is what? Is even. So the contrapositive of this statement, remember, you have to take this q and then you negate it to imply this p here is the negation of what? Of this p. So you are just reversing, you are taking this negation of q, imply the negation of p. So you are given n squared is even, then n is odd. You are just saying n, if n is odd, it implies that n squared is what? Is odd. So you are negating this even and negating this even. So what you are going to get here is that we prove this contrapositive statement directly. Suppose n is odd, which means we get these two, this n is odd. And then just do the same, you square it. And then after squaring it, you get this, and then you do what you have done previously, and then you get this. After getting this, you see that this one is an odd number, right? So hence n squared is odd. Thus the contrapositive statement is true. So the given statement is true. So your work here is just to convert it to its contrapositive. And then you prove that the contrapositive statement is true. If the contrapositive statement is true, then the original statement is also what? Is also true. I don't know if there are questions on this one. If there are no questions, go and do this exercise, which is proof there by contraposition that if n is an integer and n cubed plus 5 is odd, then n is what? N is even, which means you are going to say if n is odd, then n cubed plus this one plus 5 is even, and then you prove that. If it is true, then the original statement or this statement is true. So go and do this exercise. I just give you this example so that you'll be able to do such kind of questions. So if there are no questions, let's do the principle of mathematical induction. Principle of mathematical induction.
Hello, sir.
Yes.
May you please share the example on the contradiction, that just the example, just to share the slide of the example.
The
slide of the example for contradiction, the one with n squared.
You mean this proof by what? Proof by contradiction.
I'm kind of asking for you to just share the slide even for 2 seconds, it's fine.
Okay, you want to take the screenshot?
Yes.
No problem. No, don't worry. I am recording. I can share the video and even the slide.
No, it's okay, sir.
Yes, I can share even the slide. I can share. I'm sure I'll share. I'll just wait for it to finish to process, and then I'll download the video. I'll process the video, and then I'll share with you through my YouTube channel. So I'm sure it will be always there. This one it's a guideline. You see, there are a lot of slides on your portal. So this one is just a guideline of what you have to focus on. This one is a guideline, though there are some topics that I didn't include here. I'll just mention them at the end of this video, but there are very few. Maybe there are 3 of them, if there are many. There are 3 of them, but very few, very few. So let's do the principle of mathematical induction. Principle of mathematical induction. So given P of n is a propositional function I think you know everything about all this from your mathematical foundation. So given Pn as a propositional function, a proof by mathematical induction is two parts, which is a basic step where we show that P of 1 is true, and an inductive step where we show that for all positive integers k, if P of k is true, then P of k plus 1 is true. And then after that, you give what? You give a conclusion. So that's what on the principle of mathematical induction. It's just a mathematical way of proving given what? Given functions. So to prove that P of n is true for all positive integers n, where n is a propositional function, we complete two steps. How do you complete these two steps? You can maybe verify that P1 is what? Is true. And then after that, you do the inductive step, where you have to show that the conditional statement, sorry, I want to add someone here. I want to add someone. There's someone called Tatenda. Tatenda, are you in this meeting? Tatenda.
Arimo ndakanzi Mr. Soza.
Oh, there's Mr. Soza.
Yeah.
Sorry, inde ndakatomuti short. Anogona kutondirova izvozvo. Ndakatomuti short.
Anonzi Soza.
Oh, anonzi Soza. Alright, Tatenda Soza. Alright, it's okay. Vachiri kumboreba saka ndinombobvumiswa zvangu. Umuti short handiti usazondirova. Alright, anyway. All right, so on the inductive step, we show that the conditional statement Pk implies P of k plus 1 is true for all positive integers k. What you are just saying here, if it is true for P of k, it must be also true for what? For P plus for P of k plus 1. So if you have managed to show that P of k is true and then P of k plus 1, if you just managed to show that it is true, and then you are good to go with what? With the principle of mathematical induction. So to complete the inductive step of a proof using the principle of mathematical induction, we assume that P of k is true for any arbitrary positive integer k, and show that under this assumption, sorry, there is a phone call. I just want to take this phone call. Okay, I'm back. So I was just saying that on proof by induction, for you to complete the inductive step, excuse me, we assume that P of K is true for an arbitrary positive integer K, and show that under this assumption, P of K plus 1 must also be true. And the assumption that PK is true is called the inductive hypothesis. So you have your inductive hypothesis, which is P of K. So you have to show that P of K plus 1 is also true using this inductive hypothesis. Once you manage to prove that, we've actually done this principle of mathematical induction, and you can make the conclusion from that step. So we've got this example, which says use mathematical induction to show that 1 plus 2 plus 2 squared plus 2 to the power n is always equal to 2 to the power n plus 1 minus 1 for all non-negative integers n. So if you look at this one, you are adding we're adding 2 to the power n. We're just adding 2 to the power n. Like here, this one is 2 to the power what? 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, up to 2 to the power n. So we are adding adding here. It's adding. So it's 2 to the power 0, which is 1 plus 2 to the power 1, which is 2 plus 2 to the power 2, which is this one, plus up to 2 to the power n. So instead of adding, whenever you want to add this first 2 and then adding this one, instead of doing that, we have a formula which says 2 to the power n plus 1 minus 1. So maybe if you want to add the first 5 numbers, we can just put your n here as 5, and then maybe we go to add 2 to the power 0 kusvika 2 to the power 5. So you are being asked to show that this formula is always true for this type of addition that we have on the left-hand side. So how do you show this one? Using the principle of mathematical induction. So the solution is here. Let P of n, which is a proportional function, be the proportion that 1 plus 2 plus 2 squared up to 2n is equal to this one. So our Pn is equal to this proposition. So the basic step, remember we said for all non-negative integers. So on the basic step, make sure that the value you put here is within this domain that you will be given here. So our n is a non-negative integer. So you can do it for P of 0, you can do it for P of 1, you can do it for P of 2, but not for P of minus 1 or minus 2, because we just want non-negative integers. So here we put what? We put our P as 0. So it will be 2 to the power what? 2 to the power 0. So we are just going to put 2 to the power 0 on our n, and then here we are going to put 0 here, and then it will become 2 to the power 0 plus 1 minus 1, which is 2 to the power 1 minus 1. So 2 to the power 0, any number raised to the power 0 is always what? Is always 1. So this one will give you what? 2 to the power 1 minus 1 is what? Is 1, which is 1 is equal to 1, yes. So this completes the basic step, because we have shown that P of 0 is what? Is true. So if you put a number and then confirms that this statement is true, you can proceed to the what? To the inductive what? To the inductive step. So on the inductive steps, remember the first step there is to make the inductive hypothesis, which is P of K. And after that, you say if P of K is true, then P of K plus 1 must be also true. And then you prove that. After proving that, you'll be good to make the conclusion. So the inductive hypothesis here is that we assume that P of K, right, is true for any arbitrary non-negative integer K. That is, we assume that 1 plus 2 plus 2 to 2 squared up to 2 to the power K. Here you put a K for N, where you have N there, you put what? A K, that's P of K. And then here we've got N plus 1, it will be what? It will be K plus 1. You put a K for what? For N there. So you are saying this one must be also true. This is our P of K. That's the inductive hypothesis. So if this one is true, so P of K plus 1 must be also what? Must be also true. So to carry out the inductive step using this assumption, we must show that when we assume that P of K is true, then P of K plus 1 is also true. So that is, we must show that P of K plus 1. So remember, this one is our P of K. So for you to get the P of K plus 1, P of K plus 1, it will be now 1 plus 2 squared, plus 2 to the power K. Because remember, K plus 1, it will be the next term after what? After this K. So you put 2 to the power N, which is what? Our N is now K plus 1. So you do the same on the right hand side. You put K plus 1 here, which is equal to K plus 1, and then minus 1 here. So at the end, you are going to have 2 to the power K plus 2 minus 1 on the right hand side. And on the left hand side, you are going to have this one. So you have to prove that if we add everything here, you are going to get this here. If you manage to prove that, which means it will be actually true also for K plus 1. So if it is true for K plus 1 and true for K, then we are managed to prove that this statement or this formula can actually give us the total sum of such kind of what? Of numbers. So how do you do that? Assuming the inductive hypothesis P of K, under the assumption of P of K, we see that this one for K plus 1 is equal to what? Is equal to this one. If you look at this one, if you look at these values, this one, this part, this whole part is the same as what? Is the same as this part, right? This part is just the same as this part that we have here. Maybe I need to rub. Maybe if I rub here and here, it will be actually is this part that we have here just the same as what? Is this part that we have on the inductive hypothesis. So we can actually take this and substitute here. We can take this 2 to the power K plus 1 minus 1 and put it here. And we prove this side, this left-hand side is equal to the right-hand side. Just like that. So you end up having 1 plus 2 plus this one plus 2 to the power K plus 1. So you replace this part with the hypothesis, inductive hypothesis, which is 2 to the power K plus 1 minus 1 plus 2 to the power K plus 1. So you have to prove this one is equal to this one. So how do you do that? You can simplify this one to what? Remember, here we are just adding. If you remove this these brackets, you end up having 2 to the power K plus 1. Maybe plus 2 to the power what? K plus 1. And then minus 1. Remember, if you are adding these two numbers, if you are adding these two numbers, if you look at this one, they've got the same base, they've got the same power. It's like the same as we are saying x plus x. You get what? 2x. Because here it's just is x plus x. If you look close at this number, it's 2 to the power k plus 1 and 2 to the power k plus 1. It's just, if you add them, you get 2x, where your x is 2 to the power what? K plus 1. That's why you've got 2 times what? 2 dot 2 to the power k plus 1 minus 1. And after having this one, remember, if you multiply two numbers, if you are multiplying two numbers with the same base, you can simply add. You can simply add. You can simply, so I have to take this one. There's a hint on you. Look at it. There's a hint. What's the issue?
It was silent. It's okay now.
Okay, I was on a call. So, okay, so I was saying 2 times 2 to the power k plus 1 minus 1 is just the same as saying, let me rub this. You can simply add the powers. Like if you are saying x to the power maybe 2 times maybe x. Remember x just the power 1. What you can do, you can simply add the powers. You can say 2 plus 1 and then you get x to the power 1, x to the power 3. That's what we have done here. Is 2 to the power 1 times 2 to the power k plus 1. So you can simply add the powers. K plus 1 plus 1. That's why we've got 2 to the power k plus 2. Then minus 1. And if you look at this thing and at this thing, we've managed to prove that this left-hand side we always deduce to this right-hand side. So by the principle of mathematical induction, we've managed to prove that this one is always equal to this one for all non-negative integers. That will be your conclusion. So note that we used the inductive hypothesis in the second equation in this string of equalities to replace this part by this part. So we have completed the inductive step. Because we have completed the base step and the inductive step, by mathematical induction, we know that P of n is true for all non-negative integers n. So that is, this one is true for all non-negative integers n. That's how you make your conclusions there. That's how you make your conclusions. So this was the example 1 on mathematical induction. I don't know if there is any question on this example. Is there any question on this example? So if there are no examples here, let's just do the next example. Okay, so there is proving by divisibility. Not by proving divisibility results. Those mathematical inductions with divisibility. How do you answer such question? So mathematical induction can be used to prove divisibility results about integers. So this is an example. Use mathematical induction to prove that n cubed minus n is divisible by 3. So whenever n is positive integer, we are saying n cubed minus n is divisible by 3 whenever n is a positive integer. So remember here we are saying positive integer. So on your basis step, on the P of n, remember to put a number which is in this domain. Which is what? Which is positive integers. Which is positive integers. So solution. To construct the proof, let P of n. So you start by letting P of n denote the proposition, which is n cubed minus n is divisible by 3. So this is our proposition. Whenever n is what? Is a positive integer. So the basis step now will be for you to take any positive integer and you substitute in here, and you see if the result is divisible by 3. So the statement P1 is true because if we put 1 here, it will become 1 cubed minus 1, which is equal to 0. And we know that 0 is always divisible by 3. So this completes the basis step. So therefore, the given statement is true for what? For n is equals to 1. So you can even try to put a 2 there. 2 to the power 3 minus 2. And you try to divide it by 3. You will see that that number will be divisible by 3. So the inductive step. Let's talk about the inductive step. How do you do the inductive step? So suppose that the statement is true for n is equals to k. Remember, on the inductive step, you start with the inductive hypothesis, which is it is true for n is equal to k. So we'll be saying k cubed minus k is divisible by 3 for all n is a set of what? Of positive integers. So what we'll be saying here, the assumption that we make here is that k cubed minus k is equals to 3 times q. For what? For q is an integer in what? For some integer q. For some integer q. So what we are saying here, we are putting this, we are putting k on this item, and we have k cubed minus k. And we are saying that thing is always divisible by 3. That's the assumption. So that's the assumption. So this is how you write it. So it will be k cubed minus k is equal to 3 times q. And you call it what? Equation number 1. To put 3 times q in the sense, this one can be written in the form of 3 times something. Kana chino chikangozi 3 times something, toari chinokwanisa kutopindiwana na 3. Which means ndo zvatirikutaura kuti pana apa nechino chinozongobuda chine chino chechi 3 times something chatisiri kuziva nditi. So we need to prove that k plus 1 to the power 3 minus k plus 1 is divisible by 3. Because this one doing inductive step. So if it is true for k, it must be also true for k plus 1. So we put k plus 1 here and k plus 1 here. And we try to prove that it is divisible by what? By 3. So we have this equation, and then we have this thing. We have to prove that this one is also divisible by 3. How do you go about this one? So on the one that you have with k plus 1, we have this one, k plus 1 to the power 3 minus k plus 1. If you expand this, you are going to have k cubed plus 3k squared plus 3k plus 1 after expanding this k plus 1 cubed. And then minus this part, which is k plus 1. I was adding someone. So after that, this, if you multiply this one with a minus, you get minus k minus 1. So you find out that this plus 1 and the minus 1 is 0. And then this 3k minus k is what? Is 2k. So you end up having this thing. So if you take k cubed and you subtract k and you add k, you'll be actually doing nothing. You are adding, you are subtracting k and adding a k at the same time. Or you can actually separate this one, this 2k, and become, okay, we need to match this one. We need to match this one. So how can you make this one? So that the idea, we want to use P of k to prove. You always have to use the inductive hypothesis. So what you do there, you subtract k at the same time adding k. So minus k plus k is always equal to what? To 0. So what you are doing here, you are subtracting k and adding k. So you are saying k cubed minus k, and then tozongoti plus k kumberi kunoku. Zvamufanira tiri kuaddira k nekubvisa k. Saka pana zvataita nditi. So you end up having something like k cubed minus k plus 3k squared plus 2k plus k. But look at this one, this thing that we have created. It's now equal to what? It's now equal to this one in equation 1. It's now equal to this one, which is equal to 3q, which is what 3q. So what you do there, and if you simplify this one, it will give you a 3. So you end up having 3q plus, you factorize 3 out here, plus 3 times k squared plus q. And from here, you can factor out this 3. By factor out this 3, you left out with 3 times q plus k squared plus k. And if you look at this thing, it's now in the form or in the multiples of what? Of 3. It's now 3 times what? 3 times q. It's now in the form of 3 times q, which is the same as this one. It was now 3 times something here. So by showing this, that the resulting that we have here shows that this number is always divisible by 3. This number is always divisible by 3. It also proves that k plus 1 to the power 3 minus k plus 1 is divisible by 3. Hence, by mathematical induction, n cubed minus n is divisible by 3 whenever n is a what? N is a positive integer. I don't know if there is any question on this one. Proof by divisibility. Is there any question? Okay. So let's just move forward. I talked for a long time. So that's all on a mathematical induction. Yeah, that's all on a mathematical induction. That's all. That's all on mathematical induction. I don't think I need to add more here. Just practice, do these examples, and you can add more if you want. But first practice to remove confusion on this, and then you can end up adding more. So we are going to do trees. Going to do trees. And then maybe you end here on trees. Maybe end here on trees. Then you have to look on matrices. Yeah, we assume that you've done matrices way back, maybe in mathematical foundations. Yeah, I'm sure in mathematical foundations you've done relations. and matrices. So there is the topic of matrices is covered mathematical in that in the mathematical foundations, and then maybe you have to look on to graphs. Yeah, you have to look on to graphs. Permutation circuits. Yeah, Permutation circuits. Euler one. And then what else? Yeah, I think just those ones. Yeah, I think that's what you need to on the graphs. Just look on that one. Then you'll be good to go. So let's just do the trees. So definition: a tree is a simple graph satisfying the following. It must satisfy the following: if V and W are vertices in a T, there is a unique simple path from V to W. So you are saying if we have got vertices V and W in our tree, we must always have a simple path, not a closed one, but a simple path from what? From V to W. That one is the one that we call what? A tree, that graph. So that we call a tree. So the following graph is a tree since there is a unique simple path from any vertex in the graph to another vertex. So you can maybe go through this way, or you can go here, you can go maybe here, or what, blah, blah, blah. So let's talk about the rooted tree trees. Rooted trees model. So the rooted tree is a tree in which a particular vertex is designed or is designated the root. So you'll be having a vertex which will be called the root. So once you have such a tree, is the one that we call a rooted tree. Like here, you might have this one as a what? As our root. So you end up having the what? The children of the root. The children of what? Of the root, just going down here from this going down. So an example of a rooted tree. So it's an example of a what? Of a rooted tree. So important terminology. So there are some of the terminologies that are used in what? In trees. And they are very important. They are very important. You need to know them. So let T be a tree with the root V0. Suppose that X, Y, and Z are vertices in a tree, and that V0, V1 up to Vn is a simple path in T. Then all these statements are not related to this graph. This one is just to demonstrate what we are talking about here. So Vn minus 1 is the parent of Vn. And then V0 to Vn minus 1 are ancestors for Vn. And then Vn is a child of Vn minus 1, blah, blah, blah. I think the way I've wrote it here is not actually clear, but let me just demonstrate what you're talking about. So this one is our root. If this one is our root, there's what we call a level. So a level, we go from root, here is a level, then this one, the first children from the root is another level, then the second from those from the root it's another level, then another level, and then another what? Another level. So this one we call it level 0 on the root, and then this one is level 1, and then level 2, level 3, level 4. So you might ask you that this vertex is on which level, or this one is on which level, or this one is on which level. So this one's level 1, this one's level 2, this one's level 3, and this one's level 4. So vertices in enclosed region are descendants of U. There's what we call the descendants So all these ones, you are saying are descendants of you, because they are coming from you. You cannot go to V without passing through this U. So all these are descendants. And also V is a child of U. If we look at V, V here is a child of what? Of U. And the V, if you look at it, is a left child again. You can add that. This one is a left child and this one is a right child. The W is a right child. So V is what? Is a child of U and the W is a child of U again. Only that this one's right and this one is the left child. It's the left child. Also, we can say V and W are siblings, just like in a family. If you take this one as a family tree, so V and W will be what? Will be siblings. And the height is what? The height of this graph is 4, because we've got the level of 0 to what? To 4. So the height is what? Is 4, which is the number of levels that we have there. So normally, that's the terminology that we'll be talking about. The descendants, the siblings, or the what else? The parent or the root. So this one, V is a parent of what? V is a parent, not V, U is a parent of V. U is a parent of what? Of W. That's a parent there. And then the ancestors, maybe this root is an ancestor of what? Of these VW. And then what else? What else do I need? Also, we can call these ones leaves. These ones, they are leaves, which are at the end, they are leaves. So it's just the terminology that we use in what? In trees. Just the terminology that we use in trees. So this one is an example, which says consider the rooted tree shown below with the root V0. So this V naught is what? Is the root. What is the level of V8? You are being asked to find the level of V8. And where is V8? Where is V8? V0, V1, V3. V8, oh, this one, it's here. You are being asked to find the level of V8 and also the level of V0. And what is the height of this tree? The height as well. The children of V10. Where is V10? Here, V10 is here. The children of V10. What are the siblings of V1? Yes, we have got V1 and one the siblings of V1. And what are the descendants of V12? Where is V12? Here, you want the descendants of V12. So you must be in a position to be able to answer this question. So level of V8 and level like this one, level of V naught is 0. This one is the first level, it's 0. If you go this one, it's level 1. So if you go this one, level 2. If you go this one, maybe it's level 3. So V8, maybe it's what? It's level 4. So as you know, that level means the total number of edges along the unique path between it and the root. So as V0 is the root, so the level of V8 from the root V0 along the unique path is what? Is 3, because it covers 3 edges. And the level of V0 is what? Because there's no edge cover from V0 to V0. So it's what? It's 0. So this one is 0 and this one is 3. Yeah, so this one's level 0. This one's level 1. This one's level 2. Yeah, and this one is level what? It's level 3. Yeah. So what? It's level 3. So level 3, level what? Level 0. What is the height? Height. You said level what? Level 3. After that, we go to level what? Level 4. Is it up to level 5? So the height will be 5. The height of the tree will be 5 here. So the height of this tree is what? Is 5. Because level 0, 1, 2, 3, 4, 5. So that's it on that one. That's it on that one. And then what are the descendancies? Before the descendancies, what are the siblings of V1, the siblings of V1, V1, V2. What else? The siblings of V1. So the siblings of V1 is V3, V4, and V5. Siblings of V1. Where's V1? V3, V4, V5. No, these ones are children, not siblings. The siblings of V1 are V3, V4, V5. No, these ones are not siblings. Because V3, V4, V5, these are direct children of V1. Sibling is V1, V2, they are siblings. So this V2 is the sibling of V1. I'm sure there's an error here. There's an error here. We need to correct this one. There's an error. Then the descendants of V12, which is V17, V18, V19. This one, these are the descendants. Just down after V12, those are the descendants. This one is correct. Those are the descendants. Like if we have got this V2, all these ones are the descendants from what? From V12. If it is V0, all these one will be the descendants from what? From V0. I don't know if there are questions on this one. Are there any questions? So if there are no questions, I think I've talked for too long. Okay, binary tree. This one in fact, it's very easy. You can go through this one. Okay. Also, what you call a binary tree? The children of a node in a binary tree are ordered into a left child, a right child. So a node can have a left and a right child, or a left child only, or a right child only, or no children. You have to put a binary tree. Can I binary tree to put each and every node? Say that you're in a left and right children. You're in a left children. You're in a right children. You have to do binary what? Binary tree. So the tree made up of a left child or a node X, and all its descendants is called the left subtree of X. The subtrees are defined similar. So if you look at this one, we've got this left child, right child, left child, right child, then the right child, the left and right, the left and the right. This one is a what? This one is a binary tree. And there is what we call a full binary tree. So a full binary tree is a binary tree in which each vertex is either two children or zero. So you are saying each and every vertex must have either what? A node. It must have either both the left and the right children, or it must not have a what? A children. So for an example, this one, if you look at this, if you come to this vertex, we have got the left and the right. If you come at this vertex, we have the left and the right. If you come at this one, you've got the left and the right. If you come here, you have the left and the right. If you come here, you have the left and the right. Here, you've got the left and the right. Here, the left and the right. Except for these leaves only. So that's the full binary tree. And we've arrived at the end of our tutorial. So that's all for this tutorial. I don't know if there are questions on what we have done here. Are there any questions?